The production of oil and gas is a complicated process that is abounding with challenges. Sand production in wells has plagued oil and gas companies for decades, and modern fracking practices have made sand production even more prevalent. The choke valve is designed to take the brunt of the pressure off of the line components, increasing their life and yielding significant benefits. By restricting the flow to a very small opening or orifice, choke valves reduce well pressure and control production rate, creating downstream or back pressure.
There are four main elements of concern in a choke valve:
inlet, outlet, trim, and throttling mechanism.
Choke valves are continuously subjected to pressure drops, corrosion, and erosion, which can cause expensive breakdowns. Erosion is the process of material destruction. A well stream typically consists of a mix between oil, gas, water, sand, and other various particles. When all of these elements hit the internal surface of the choke valve, it can cause erosion. The material properties of the choke valve and the impact velocity and the angle of the fluid particles affect the rate of erosion. Let's discuss how erosion affects several choke valves currently in use. The simplest choke valve is the positive type. The positive chokes contain built-in orifices called beans. To reduce erosion, these beans are often lined with tungsten carbide. However, these chokes are still susceptible to high rates of erosion.
An adjustable choke can compensate for some degree of wear, but a positive choke cannot. The pressure must be isolated so that the valve body can be opened and the bean removed. This is time-consuming and expensive.
For frequent flow regulation, an adjustable choke will work the best. One of the oldest designs is needle and seat. This valve has a tapered lead on its stem
To restrict the opening by closing the needle against the tapered seat.
The seat is typically threaded into the body, and the throttling is achieved by rotating the handle on its rising stem.
A narrow opening between the needle and the seat restricts the flow and causes an increase in fluid velocity, since velocity is a function of volume over the area. The seat surfaces act as restrictive devices, which subjects them to a higher friction and deterioration.
Multiple orifice valves, or disc-style choke valves, provide improved flow control and shutoff capability. When these openings are perfectly aligned, the flow rate is maximum. When these openings are offset by 90 degrees, it shuts down the flow completely.
Erosion is common around the edges of the holes. The high-velocity jets from the throttling ports flow into the valve outlet, resulting in high potential of valve body erosion. As the discs wear out, the valve's shutoff function could be lost.
Our next choke valve has fixed cage and internal plug. A stem connected to the cage allows the cage to be moved up and down by the rotation of the wheel, changing the size of the opening for the flow.
Inside the choke, fluid circulates in the annulus between the body and the cage.
The location of the cage openings forces the streams to collide in the middle. Impinging streams cause hydrostatic back pressure and allow using fluid energy against itself, resulting in minimal wear of valve material.
The cage and plug choke valves work best when the cage ports are fully open, which allows the high-velocity jets to be perpendicular to the valve axis. Otherwise, the jets are directed towards the valve outlet and cause its erosion over time.
Let's move on to the most advanced choke valve, the cage with external sleeve. This valve is best for high pressure drops and high sand concentration applications. Moving the seat to the outside where the fluid velocity is lower, reducing wear to the throttling surface and improving seat life. Reduction of valve outlet erosion is another important element of the external sleeve. It's achieved by directing the fluid exiting the throttling port into the valve trim and away from the valve outlet.
Let's compare erosion in the last two choke valves. Masterflow tested the effects of erosion at their state-of-the-art testing facility by placing 2 valves in series, subjecting both to identical sand and flow rate conditions. Masterflow engineers encountered some interesting observations. As the fluid began to move towards the vena contracta, where the diameter of the stream is smallest, the fluid in the internal plug design accelerated in the cage port and directly impinged onto the exposed internal plug, resulting in an extensive material loss. The seat integrity of the internal plug was lost within 30 minutes. The external sleeve seat feature was outside of the cage, away from the high-velocity turbulent fluid zone, so it lasted throughout the 10-hour test.
This valve's material loss was only 4.23 grams. In stark contrast, the internal plug design lost an astounding 12.75 grams. That's more than 3 times the material.
When the engineers compared the external sleeve to the internal plug, they observed that the plug lost 54 times more material. By placing the seat upstream of the throttling ports, the external sleeve valve was able to maintain shutoff capability by the end of testing and showed 20 times longer seat life than that of the external plug design. Also, the material loss of the outlet sleeve was 3.2 times higher, and the depth loss was 4 times larger in the internal plug valve.
This was explained by the CFD analysis that showed high-velocity fluid jets in the internal plug were directed into the outlet. By contrast, in the external sleeve valve, they were directed towards the valve trim, away from the outlet.
Now let's discuss the role of trim material in resisting erosion. For a long time, choke manufacturers selected their trim material from a nickel or cobalt binder tungsten carbide. To address both corrosion and erosion, carbide vendors began using a composite binder, a mix of cobalt, nickel, and chromium in a tungsten matrix. This material is traditionally referred to as tungsten carbide. In the tests conducted using the Masterflow erosion loop and several third-party labs, the trims made out of 5CB, a premium-grade tungsten carbide, demonstrated the highest erosion and corrosion resistance as well as toughness.
How better choke valves can affect your company's bottom line, you may ask? A Masterflow customer replaced the needle and seat choke valve at their shale gas site and shared the results. Before switching to the external sleeve choke valve, the company had to shut down production every 12 days to inspect or replace their choke valve. By utilizing Masterflow's external sleeve and cage design, they were able to extend this period to 80 days. At the same time, repairs-related expenses reduced by 65% using the external sleeve. And most importantly, the company was able to increase their production rate from 7 million standard cubic feet per day to 10, due to the improved erosion resistance by Masterflow's external sleeve and cage choke valve. Taking all of the factors into account, the producer was able to turn a $1,500 investment into a staggering $3.4 million of increased ROI. With less interruption in production and less time spent on costly maintenance, you can increase your profit exponentially. It's time to master the flow. Masterflow.
SmartView is a product that can interface with different I/O types, and then it can take that information, it can display it on the screen, log it for future reference, and it can be used to display alarms or create alarms when the process is operating outside of its normal expected parameters.
Some of the specific features include its wide operating temperature range, -40 to +70 degrees Celsius, the ability to access the SmartView from anywhere in the world using the Ethernet connector. Also, the sunlight readable display is an excellent feature. The SmartView is designed to be compact and rugged, so it can be installed on an operator's console or a panel near to industrial equipment or farther away if needed. What makes it unique is that it really is an all-in-one package. It includes a lot of features that other products might have distributed over more than one device. The Smart View can help improve workflow by allowing the customer to save configuration data and transfer it to other units. The data that is measured and logged by the Smart View can be extracted by the USB port, and the unit is also field upgradable.
It's really user-friendly. It has built-in configuration firmware, which allows the user just to get up and running in a very short period of time, and the results can be immediate.
When you buy directly from DieCore, you're buying directly from the design team. So we understand the ins and outs of the device, we designed it from the ground up, and we can ensure that it works in your application.
StreamFlow has taken the term smart ESD and refined it into what we call the ESD-EHX, which is an emergency shutdown system combined with an integrated electro-hydraulic package, and the X represents the smart aspect of it.
What the smart ESD has allowed us to do is to take a very basic ESD and take it all the way to the point of being totally autonomous. This system can ultimately think all by itself, and it brings that very crude ESD system right up to the 21st century.
Smart ESD allows autonomous control of the surface safety system. What that means is you can control it remotely from virtually anywhere in the world. It provides system diagnostics. It allows edge computing, cloud-based communication, so you can minimize the number of visits to the site to check on the health of the unit.
In the past, when you wanted to know what was going on with your well site ESDVs, you had to put a man in a truck. He had to drive out there in the snow, in the desert, in the wherever, go into possibly hazardous situations and see what's going on with the ESD. Now, I can do this on my laptop. I could have a well in Abu Dhabi, I could be here in Edmonton, I can analyze that well, I can look at it, I can do all that right from here. Something that StreamFlow did very, very well is the way they designed the system to be retrofittable to our existing equipment. You don't want to have to replace your entire emergency shutdown system to make it intelligent, to make it autonomous. What we've done is we have modular designs. We can take our old ESDs and then we can adapt all this equipment to it.
The StreamFlow ESD-EHX utilizes design and manufacturing from several StreamFlow companies. By bundling this technology and capabilities together, it sets us apart from the competition.
StreamFlow has incredible skill in its engineering group. We have incredible talents, and that allows us to design anything we want.
A choke valve is one of the most important but least studied components of the wellhead. It is also the most critical element of the flow line that directly impacts production and revenue.
In the oil and gas industry, choke valve design is governed by API 6A and 17D standards. Choke valves are used to control flow rate and pressure drops. Reducing the flow channel with an orifice accelerates fluids, sometimes to sonic speeds. For that reason, the design of a choke valve must consider the effects of erosion, high fluid velocity, and significant pressure changes. Choke valves are categorized by their application, including drilling, injection, and production. Drilling chokes are employed to control high pressure fluctuations during the well drilling process. Injection chokes are usually used to control flow rate and back pressure in the pipelines going into the injection wells, including gas and water injection systems. A production choke is typically used for well optimization or to reduce the wellhead pressure to a level that is safe for transportation. All choke valves face three main problems: erosion, hydrate formation or freezing, and flow controllability.
The flow rate is controlled by restricting the flow to a small opening or orifice. The degree and level of control depend on three main factors: choke trim design, actuator resolution, and measurement accuracy. Other factors include valve clogging and wear due to erosion and corrosion.
Let's discuss the flow characteristics of 4 types of choke valves. The needle and seat has a tapered lead on its stem to restrict the opening by closing the tapered seat. The throttling is achieved by rotating the handle on its rising stem. Due to the tapered design of the needle, a small rotation of the stem handle can cause significant change to the orifice opening. This choke design doesn't provide a high degree of control. When the choke is open halfway, you experience full flow, losing most of your control. The multiple orifice valve design allows for proportional changes in the flow. This type is most applicable when the upstream and the downstream flow are controlled at fixed points. This is not the case in nature. As the well is unloaded, the upstream pressure comes down and the downstream pressure rises. In a refinery application, for example, the upstream pressure is typically fixed. The cage with internal plug and external sleeve choke valve designs are both characterized by equal percentages or modified parabolic control. They provide a gradual response in the lower portion of stem travel, delivering high level of initial control. This brings the well on stream. As the valve is open and the flow increases, this level of control is maintained throughout the stem travel, resulting in high turn-down ratio, high repeatability, and precise flow control.
This is imperative because a well-controlled flow allows you to ramp up your well slowly. A rapid well ramp-up can destabilize it, potentially causing a collapse and reducing well's productivity index. Avoiding damage to your most valuable asset, the reservoir, is crucial.
MasterFlow's standard trim provides a high level of control over its life. The smaller, lower ports provide the initial 15% of the control range, while the larger ports provide the valve's overall capacity. This results in equal percentage flow characteristic curve and high liquid pressure recovery factor. To compare valve capacities and to size valves for specific applications, several coefficients are used. The first one is a flow coefficient. Flow capacity testing establishes a flow curve over the valve travel and provides a basis for comparing trim styles. Each valve type has a unique curve based on internal geometry. A greater restriction provides better velocity management but lowers the flow capacity. When the seating area is close to the throttling area, the erosion issues may occur, as frequently happens with the needle and seat valve. MasterFlow solved this issue by incorporating a dead band area in the design of the external sleeve and cage choke valve. The dead band ensures that the throttling area is far from the seat, resulting in an area of zero flow. MasterFlow's custom trims could be designed for a specific pump curve, providing high loss coefficients at low flows and low loss coefficients at high flows. Custom trims allow to eliminate the need for parallel valve operation and therefore reduce maintenance while increasing reliability and controllability. In production, only inlet and outlet pressure values are measured. However, inside the valve at the throttling point, the pressure is much lower. This is designated as the vena contracta pressure. That brings us to another important factor of the choke valve selection process, the liquid pressure recovery. This is the ratio between the pressure drops and the difference between the upstream and the vena contracta pressures.
If the pressure in the choke falls below the vapor pressure of the liquid, cavitation may occur. When this happens, the pressure is greatly reduced in the valve. The susceptibility to cavitation is governed by the valve FL number, which determines how low the pressure can get inside the valve. In extreme cases, freezing of gas may occur in a choke valve due to hydrate formation.
As you can see, the cage with the external sleeve design provides a higher FL over a wider range of valve openings. The higher FL number means a lower chance of cavitation and consequently the risk of damage. For demanding applications with high pressure drops, two-stage trims could be used. They consist of concentric cages which handle pressure drops in stages, reducing pressure dip at the vena contracta. This results in better control over the cavitation and noise.
MasterFlow's multi-stage trims are available in service-specific materials, including the proprietary 5CB tungsten carbide for higher erosion and corrosion resistance. Multi-stage trims can also be engineered to provide custom flow curves.
The effects of staging can be seen on these graphs. When more than two stages are needed, a labyrinth style trim is employed. It features an internal plug and a labyrinth cage that allows a smooth transition between cage ports. Also, controls the velocity throughout the labyrinth. These trims are available for liquid, gas, and multi-phase applications. The trim cage is compression loaded and constructed as a solid element of tungsten carbide for durability and ease of service. The custom port designs are available to optimize performance depending on the fluid type and gas-oil ratio. This chart demonstrates a few possible flow control curves. However, MasterFlow can provide almost any control characteristic to fit the needs. MasterFlow's custom trim designs go through extensive CFD analysis where the control characteristics are evaluated, feeding the information back to the engineers. It's time to master the flow. MasterFlow.